In this lecture video, we'll begin the conversation about analysis of variance, also known as ANOVA, and we begin with one-way ANOVA. Analysis of variance, or ANOVA, is a method of testing the equality of three or more population means by analyzing sample variances. We are testing to see if three or more population means are equal to one another. And even though we're analyzing variances, it's really a test for equality of means. A treatment or factor is a property or characteristic that allows us to distinguish the different populations from one another. In one-way ANOVA, the sample data are separated into groups according to only one treatment or factor or characteristic. We have a few requirements for one-way ANOVA. The first is that we require that the populations have distributions that are approximately normal. However, this is a pretty loose requirement. A second loose requirement is that the populations have the same variance or standard deviation. The samples need to be simple random samples of quantitative data, and the samples need to be independent of one another. And finally, since we're talking about one-way ANOVA, the different samples need to be from populations that are categorized in only one way. When we are performing a one-way ANOVA, the null hypothesis is that the means are equal to one another. Here I have mu1 equal to mu2 equal to mu3, but we could have more than 3 means. The alternative hypothesis is that at least one of the means is different from the other. The test statistic in this case takes into consideration some very interesting relationships within the data set. The numerator is equal to the variance between the samples, and the denominator is the variance within the samples. Let's take a closer look at this notation. S sub x bar squared is the variance of the sample means. We're looking at how much variability there is among the 3 or more sample means. SP squared is the pooled variance. This acts as a sort of average of the sample variances. In our first example, we'll calculate the test statistic by hand so you can get a better idea of what we mean by the variance between the samples and the variance within the samples. Lastly, notice that our test statistic is an F statistic. ANOVA methods require the F distribution. In your textbook, that's table A5, and it has these properties. The F distribution is not symmetric. The values cannot be negative, and the shape depends on 2 different degrees of freedom. And here's how we find those 2 degrees of freedom. First, we let K be the number of samples, and N be the size of the samples. The first degrees of freedom we refer to as the numerator for degrees of freedom. And it's equal to K minus 1, 1 less than the number of samples. The second degrees of freedom we refer to as the denominator for degrees of freedom. And it's equal to n minus 1, 1 less than the sample size. Let's take a look at our first example to help us better understand this test statistic. In this example, notice that we have 3 samples from 3 populations. That means that our value for K is equal to 3, the number of samples. And since each sample is size 4, our n is equal to 4. Our calculators do have the ability to compute the test statistic for us. However, for this example, I am going to compute the test statistic by hand, so we have a chance to work with the variance between and the variance within. The test statistic F is equal to the variance between the samples divided by the variance within the samples. Let's start with the numerator. The variance between is equal to n times the variance of the sample means. Let's think about what this variance of the sample means is. Sample 1 has a mean of 5.5. Sample 2 has a mean of 6, and sample 3 has a mean of 6. So we're looking for the variance of these 3 numbers as their own data set. We'll start by calculating the mean of the sample means, x double bar. This is equal to the sample means, 5.5, 6, and 6, divided by 3. So the mean of the sample means is equal to 5.8333. To calculate the variance, we need the difference of each data value and the mean squared, all added together, divided by n minus 1. So we need our first data value, x1 bar, minus the mean of the sample means, x double bar squared. And we need the difference between the second data value, x2 bar, and the mean, x double bar. And finally, the last data value, the mean of the third sample minus the mean of the sample means, x double bar squared. We add all of those together and divide by n minus 1. And filling in our values, we have something like this. Putting this into our calculator, we find that the variance of the sample means is equal to 0.0833. So now we have what we need for the numerator of the test statistic, the variance between the samples. Now we can work on the denominator, the variance within the samples. This is SP squared, or the pooled sample variance. And it is the mean of the sample variances. In other words, to find SP squared, we need to add up the 3 sample variances and divide by 3. Filling in our values, we have 3 plus 2 plus 2, all divided by 3. This gives us a pooled variance of 2.3333. Now that we have the numerator and the denominator, we're ready to calculate the test statistic. The numerator is equal to n times the variance of the sample means, and the denominator is equal to the pooled sample variance. N is equal to 4. The variance of the sample means we found to be 5.8333, and the pooled sample variance we found to be 2.3333. Putting this into our calculators, we find that our test statistic F is equal to 0.1428, rounded to 4 decimal places. So that's the idea of this type of test statistic. We look at the variance of the means and the means of the variances. Let's move on and perform the one-way ANOVA with this sample data. Here's our claim. Our claim is that the 3 samples are from populations with equal means. Let's use a significance level of alpha equal to 0.05. The first step is to determine the null and alternative hypotheses. The null hypothesis, H0, is the statement of equality, that the means are equal to one another. And the alternative hypothesis, H1, is that at least one of these means is different from the others. Step 2 is to calculate the test statistic. In this example, we calculated our test statistic by hand. We found that F was equal to 0.1428. But let's look at how we would calculate this using our calculators. The calculator function that we will use is called ANOVA, and it requires that we have our sample data in lists. So we'll start by going to Stat, Edit, and entering our 3 samples into lists 1, 2, and 3. Now we're ready for the ANOVA function. We go to Stat, Tests, and scroll down to find ANOVA. Pressing Enter will paste ANOVA and the first parenthesis on the home screen. We need to enter the lists where the sample data is found, separated by commas. We put our data into lists 1, 2, and 3. So we'll type list 1, comma, list 2, comma, then list 3. Finally, we'll close the parentheses and press Enter. This performs a one-way ANOVA for the sample data in those lists. We found a test statistic F of 0.1429, which is almost identical to what we found calculating it by hand. We're also given a p-value of 0.8688, and we'll need that in step 3. So let's head back to our example. Step 3 is to calculate the p-value. Our calculators gave us a p-value equal to 0.8689, which is significantly larger than our value for alpha. So we're ready to state our conclusion. Since we have a large p-value that's greater than our level of significance, we fail to reject the null. And in failing to reject the null, we have failed to reject the idea that the means are equal to one another. In other words, it's possible that the means are all equal, that these samples do in fact come from populations with equal means. Let's take a look at a second example, and we'll run straight through the hypothesis test without calculating the test statistic by hand. Here, the data that we are given is scores for levels of difficulty with different samples of reading materials. The samples here are from The Bear and the Dragon by Tom Clancy, Harry Potter and the Sorcerer's Stone by J.K. Rowling, and War and Peace by Leo Tolstoy. We're going to see if these three books have different reading levels or if they are in fact the same. And we'll do this by running an ANOVA. We'll consider the data from Clancy our sample 1. Rowling sample 2, and Tolstoy sample 3. It's not a requirement that we look at the descriptive statistics for these three samples before performing the ANOVA. However, let's glance at our three samples. If you put the values from the first sample into list 1, we have a sample size N1 of 12, a sample mean X1 bar of 70.73, and a sample variance S1 squared equal to 128.28. If we do the same for the second sample, we again have a sample size N2 equal to 12, a sample mean X2 bar equal to 80.75, and S2 squared equal to 21.92. And finally, if we repeat this with the third sample, we have a sample size N3 equal to 12, a sample mean X3 bar equal to 66.15, and a sample variance S3 squared equal to 61.75. Even though we are analyzing variances, remember, we're really interested in comparing the sample means. We want to know if the population means are equal. This is what we're really interested in comparing. Are these three close, or are they different enough to say that these three samples come from populations, books in this case, that have different population means? Are they different enough to justify saying that they have different reading levels? Let's perform the one-way ANOVA. The first step is the null and alternative hypothesis. The null hypothesis is that all three population means are in fact equal to one another, and the alternative is that at least one is different from the others. The second step is to calculate our test statistic, and we'll let the ANOVA function in our calculators do that for us. We'll head back to our lists, clear out the data from the last example, and enter our new data. Then we can head to Stat, Tests, and ANOVA. Once again, our samples are found in lists 1, 2, and 3. So we'll type list 1, comma, list 2, comma, list 3, and close the parentheses. Pressing enter gives us the values for our hypothesis test. Notice that our test statistic F is equal to 9.4695, and our p-value is equal to 5.6 times 10 to the negative fourth. Let's take this back to the example. We have our test statistic F equal to 9.4695. We also have our p-value equal to 5.6 times 10 to the negative fourth. That's equal to 0.00056, or 0.0006 rounded to 4 decimal places. We're ready to state the conclusion. Since our p-value is small, that is, it's less than our level of significance, 0.05, we reject the null hypothesis. So we reject the idea that the three population means are equal to one another. And instead, we can conclude that these samples come from populations with different means, different reading levels of difficulty. One important note. Running the ANOVA told us that these three population means are not all equal to one another. They're not all the same. However, it does not tell us which one is the one that's considered significantly different from the others. We would have to run a follow-up test with these three samples to determine which one is significantly different from the others. That concludes this lecture video. We introduced the idea of ANOVA and performed one-way ANOVA.